Welcome to this new video. It's focused on the linear homogeneous differential equation with constant coefficients. But before that, remember in the previous video, when we introduced the concept of differential equation, we talk about first order differential equation. We also discuss the orders of differential equation, right? We discuss when the equation is linear and when the equation is non-linear. So in this video, we want to focus our attention on the case of linear homogeneous differential equation with constant variable, okay? So you should note the difference here that it is an homogeneous equation, not non-homogeneous. Remember in the previous video, when we talk about the non-homogeneous equation, we have the right-hand side of the equation should be non-zero function, okay? So, but in this case, it is 0 when we talk about homogeneous. So I just wanted to call your attention before we move on. All right, to solve the linear homogeneous differential equation, we need 3 steps, okay? So the first step is to find the auxiliary polynomial. What does that mean? We have to introduce this to choose the general form of the solution. And in this case, if we choose the general form of the solution as lambda x, then we derive this function and substitute in the equation, okay? And this will lead us to a polynomial p lambda. This is the first step. The second step now is to solve this polynomial, obtain the roots. So we find the n root of this polynomial of p of lambda. And finally, we write down the solution to the differential equation as a linear combination of n linearly independent functions. Okay? So write down the solution. All right, once we understand this step, we can take some example and see how to apply this. But before we take the example, we will see we have different scenarios where we have real solutions. So when we solve this polynomial, we can have a real solution. We also have some cases where we will deal with complex roots, okay, of this polynomial. And we also have some cases where you have repeated root, okay. So, but let's start with the simplest case. Let's start with this. All right, this is an example. Find and solve the auxiliary polynomial associated to this equation, okay? And write down the solution to the equation. That's what we call here solve the equation. Let's follow this step and see. The first step consists of, we assume that this solution, initially we assume that the solution has this form, e to the power lambda x. Then we find the first derivative, this is lambda times e to the power lambda x, and the second derivative will be lambda squared times e to the power lambda x. All right, let's take this to the equation and see. If we substitute this second derivative, first derivative, and this value to this equation, what do we obtain? We have lambda squared times e to the power lambda x minus 3 times lambda times e to the power lambda x plus 2 e to the power lambda x is equal to 0. All right, at this stage, we can factorize. Let's write it like this. E to the power lambda x bracket lambda square minus 3 lambda plus 2 is equal to 0. We know that this e to the power lambda x cannot be 0 because it is our solution, the form of our solution here. So we know that e to the power lambda x is different from 0. This means that it's only lambda squared minus 3 lambda plus 2 is equal to 0. Okay? This is then our polynomial. Let's call this p of lambda. So you find p of lambda, lambda squared minus 3 lambda plus 2 equal 0. All right, we want to find the root of this polynomial, p of lambda. So you can factorize this or you can use the discriminant method to solve this. It's up to you. So if you factorize this polynomial, you have lambda 1 bracket lambda minus 1 lambda minus 2. Okay, if we expand this is lambda square, this is minus 2 lambda, this is minus lambda, and the last one is 2. So this is the root. From here we can solve for lambda is equal 1 or lambda is equal 2. Second step completed. We find the n root of the polynomial. N root here, this equation 1 is n order polynomial. That's why we are talking about the n root here. But in our case, we have a second order polynomial. That's why we have 2 roots. Okay? So let's move to the next step. We have to write down the general solution associated to this equation. So let's call this step 1. Step 1. This is step 2. This is step 2. And now for step 3, we want to write down this general solution. The one solution here is e to the power, if we substitute lambda by 1, this is e to the power 1 times x. And another solution here is y is equal e to the power 2x. Okay? So the general solution is just a linear combination of these two. So this is y is equal a times e to the power x plus b times e to the power 2x with a and b in R. Okay? So this is the final solution. This is the final solution to this differential equation. So I hope you understand this. You just have to follow these 3 steps, and any differential equation on this form you should be able to solve. But hold on, it's not all. We still have to discuss what if the roots here are complex, and what if the roots are repeated. So we have to discuss those cases in the next video. So I look forward to seeing you there. Thank you.